Now let's extend our regressions to include multiple independent variables. We'll move from doing simple linear regression to multiple linear regression. And we'll use this data set, and this is showing monthly iced coffee sales in our coffee shop. Column A is the demand in cups of iced coffee sold per month. The time period is the month, and that's in column B. Column C is the forecasted average temperature for that month, and this is known in advance, so I can use it in the forecast. Column D tells me the year. Column E is the month name, and I have a flag in column F that's saying whether school is in session or not. This coffee shop is located next to a big school, and so this tells me whether the school is in session, because I might have an inkling that students drink iced coffee. So what am I going to do? Let's develop a number of different models. The first model we're going to test is looking that we assume there's a level for the demand, that's beta naught. We think there's a trend, that's beta 1, that's a function of the time period. And then we also think there's this beta 2, which is the impact of temperature. So my variable x2 is going to be the forecasted temperature. So this is what my regression equation looks like. I'm going to use the linest function following the earlier directions. The only difference is when I get to the known x's, I'm going to do both of these columns. Right? I highlight both of them because in the linest function, your x variables, your independent variables, need to be adjacent to each other. So they have to be next to each other. Also, when I'm activating this in Excel, instead of expanding the cells to 5 rows and 2 columns, I need to go to 3 columns. Why? Well, I've got another explanatory variable here. So actually, the equation is I always do 5 rows, but I want to expand over k plus 1 columns. So that's each explanatory variable plus the intercept. Okay. So if you do this and everything works out right, you're going to get some output. Now it looks a little bit different, but it's not that different. Some things will always be the same. One is the top right cells will always be the intercept and the standard error of the intercept. Also, the bottom 6 cells will always be these, the R squared, the standard error, the estimate, the F statistic, which we're not really talking about, the degrees of freedom, sum of squares of the residual, and sum of squares of the error. Those won't change. What does change is every explanatory variable I add in adds 2 more cells here. And so if I have a third, this will just shift over again. Now you get these NAs because there's nothing in those cells. All right, so let's look at this and let's interpret the results. So for my data set, I've got 24 observations, n is 24, k is 2, remember, because the intercept is not an explanatory variable. Gives me a degree of freedom of 21, or I could just look for it right here in the table that the matrix, the linest function, gives me. And so first question I want to ask, how good is the overall fit? Well, I look at the R squared, right? This is the R squared, and it tells me 0.78. Remember, this goes from 0 to 1, so it's not bad. It's above a 70%, so it's acceptable. So then the next question I ask is, what about the individual variables? Because what this linest function has given me the estimates, remember where this is beta naught, this is the trend in coffee, additional cups of iced coffee sold per month, and this is the temperature effect. So this is saying my level is 3,254 cups of coffee a month. Every new month I sell about 52 more cups. Pretty good. It's an upward trend. And then the B2 is saying for every degree that it gets warmer, it's expected to get warm for that month, I sell about a quarter less of a cup of coffee. So this is saying negative, that there's a negative correlation. So now we want to check, since we looked at the goodness of fit and that was okay, I want to look at these individual coefficients. So I'm going to run t-tests. So let's look at the first one for the intercept, and all I'm going to do is do the t-statistic, which is just the estimate, right, of the estimate over the standard error for that. And I just rounded the terms here. Instead of 3,254.81, I just did 3255 over 175, and it gave me a t-stat, or a t-statistic of 18.6. Plug that into my t-dist function with a degree of freedom of 21 and a two-tailed test, and that number is tiny. It's much smaller than 0.0001. So I'm good there. I do the same thing for the trend, right, using these values. and I get another t-stat. The p-value is going to be very low. And then I do it for the temperature effect, doing the same thing. Now the only difference is that I actually only want to put the absolute value in here. If you put a negative value into the tdist function, it'll give you an error. So make sure you put in the absolute value. But it also gives you a value of 0.9223. While these, for the intercept and the trend, are very acceptable, temperature is not. And so it fails that t-test. We cannot reject the null hypothesis that the temperature effect coefficient should be 0. It's not really doing anything. The variance is so much bigger than the mean. So what do we do with this? Well, we try the model without the temperature effect. This is kind of what you do with regression. You test different models. So let's test another one, and we'll call this one Model 2. Same data set. Nothing has changed there. But on my model is going to be a little bit different. I'm only going to do level and trend. So I'm back to a simple regression model. And so I do the line-est function, and I get this result. And so I look at the model fit. Model fit's about the same, 0.78. We'll look at that a little closer in a second. And the variables, yeah, I'll let you test those yourself, right? You're doing the t-statistics, but they're both much lower than 0.0001. So the p-value is good, so it's an okay fit, and each of the variables are statistically valid. However, let's look at something a little closer. Let's compare the goodness of fit, the r-squared, between the two models. And at 2 decimal places, they were very similar. But let me expand out to go to 5 decimal places. So for Model 1, that's where I had the level, the trend, and the temperature effect. My r-squared was 0.77594. For Model 2, where I just had the level and the trend, it was 0.77584. Slightly worse. I mean, tiny worse, but still a little bit worse. Why would my model get worse? Why is Model 2 better? Right? We said it was better. It looked better. Both the variables were statistically valid. When the r-square is lower, isn't the r-squared supposed to tell us the goodness of fit? So this seems kind of strange, because we said Model 1 we probably don't want to do it because its temperature effect doesn't really make sense, but the r-squared's better. Okay, what is happening here? Well, the thing is that the r-squared value will never get worse and will usually improve if I add more variables in. So I could throw the entire kitchen sink in there and my r-square will never get worse. It'll always get a little better because I'm explaining a little bit more. But what you need to do is to modify it, and you need to adjust it to take into account the number of explanatory variables you're using. And that's why we use the adjusted r-squared. And that's this metric right here where we take the old r-squared, right? So we do 1 minus r-squared, and we multiply it by this term. Now let's look at this for a second. All that we're doing is multiplying it by this ratio n minus 1, which is the degrees of freedom for the error, divided by n minus k minus 1, which is the degrees of freedom for the whole model. So as I increase my k, what's going to happen? This denominator gets bigger, so therefore this whole value gets smaller. So as my k goes up, this adjusted will drive that r-squared, the adjusted r-squared, down. So if I do the adjustments here, we can see for Model 1, it's 0.754, and for Model 2, it's 0.765, which is better, right? And so that's what we wanted. And so the idea here is you should always look for the adjusted r-squared. Now it's kind of a pain that we have to do it by hand here. Any statistical package will always give you this adjusted r-squared. Always use the adjusted r-squared.